Thank you for giving us the opportunity of presenting our work in this conference. This work is about multifunctional graphene oxide two-dimensional oligoglycine Tectomer hybrids. This is the outline of my talk. First, I will explain what oligoglycine tectomers are. The versatile chemistry of biomolecules provides an intriguing and sophisticated means to incorporate nanobuilding blocks into biological environments, as well as into supramolecular structures by self-assembly. Such processes can be suitably controlled by tuning the experimental conditions such as pH, solvent, temperature, and composition, offering new opportunities for designing smart functional materials and nano devices for a range of biological and technological application. Oligoglycines are examples of synthetic peptides with exceptional self-assembly capabilities. Amino-terminated bi- and tetraantennary oligoglycines are able to assemble into rigid two-dimensional structures called tectomers. The stability of these assemblies is explained by the formation of hydrogen bond network extended in 2 dimensions, and by the inaccessibility of water molecules to the internal regions of the assemblies, hydrophobic effect. Interestingly, though tectomers formation can take place in solution, it has been reported that the assembly process proceeds 2 orders of magnitude more rapidly on a mica surface. pH shifting towards alkaline conditions triggers the protonation of terminal amino groups and the loss of the associated electrostatic repulsion, resulting in extended tectomer formation. Tectomers offer amino groups in the basal plane that are expected to establish strong interfacial interactions with a variety of nanomaterials and substrates. Thus, tectomers offer exciting opportunities for the development of new functional materials and coatings. Microscopic characterization of oligoglycine tectomers is shown in this figure. The two-dimensional nature and micrometer size of the tectomer assemblies resemble the structural features of liquid phase exfoliated graphene or other inorganic layered materials. AFM studies for biantennary QT tectomers reveal that the molecules assemble into a single layer platelet with an average thickness of 5.6 nanometers, which exhibit Angstrom scale roughness. For tetraantennary, for T tectomers, the thickness for individual platelets is 4.5 nanometers. Wettability studies conducted on tectomer-coated glass substrate show that the deposited tectomer films provide enhanced hydrophobicity upon peptide functionalization. The enhanced surface hydrophobicity is due to the formation of strong electrostatic interactions between tectomers and hydrophilic surfaces, leading to the exposure of the non-polar sites on the top. We have recently demonstrated the capabilities of tectomers as efficient pH-sensitive nanocarriers for controlled loading and release of the fluorescent anti-cancer drug coralline, making tectomers extremely attractive for biosensing and therapeutic applications. Moreover, the loading of guest molecules into tectomers facilitates the protection from rapid photochemically induced degradation. Also, the more potent anti-cancer drug doxorubicin strongly attached to tectomers, as shown by confocal and fluorescence microscopy. A patent was filed on the development of these tectomer-based nanocarriers. We also reported on the functionalization of transparent silver nanowire electrodes with Tectomer nanosheets, where the Tectomer coating significantly increases the overall electrode electrical conductivity through mechanical squeezing of wire-wire junctions in the silver nanowire network. The strong silver nanowire Tectomer interaction results from the donation of electron density from Tectomer amino groups toward the wires. Moreover, these Tectomer coatings provide enhanced electrode hydrophobicity and protect silver nanowires against oxidation and degradation when exposed to atmospheric conditions. Thus, these materials are promising for transparent, flexible electrode applications. Our results led to a patent, which was licensed by the company Untitled Nanotechnologies. Tectomer hybrids with carbon nanomaterials and nanoparticles. We have shown previously that carbon nanotubes can be successfully dispersed using amphiphilic alpha helix and beta sheet peptides. Guided by this experience, we first attempted to disperse pristine HIPCO single-wall carbon nanotubes and multi-wall carbon nanotubes in water using Tectomers. However, these peptides were not successful at dispersing pristine carbon nanotubes. TEM characterization of these samples confirmed that there is very little interaction between Tectomers and non-functionalized carbon nanotubes. Tectomers lay on top of the carbon nanotube bundles rather than coating the carbon nanotubes. In contrast, when using carboxyl surface modified multi-wall carbon nanotubes, uniform and stable water dispersions were obtained with both B antennary 2T and theta antennary 4T Tectomers. TEM and AFM studies show extensive peptidic coating on the carboxylated carbon nanotube surface. In addition, these figures reveal that Tectomers adapt to the nanotube curved surface. According to XPS spectra, protonated amino groups are neutralized during the hybrid formation process. Thus, electrostatic interaction between protonated amino terminal groups of oligoglycine and the negative charges of the carboxylic acid group on the carbon nanotubes account for the hybrid formation. Donation of electron density from non-protonated amino groups in Tectomers to the pi system of carbon nanotubes might additionally contribute to the observed shift in the peak at 400 electron volts in XPS spectra. We then investigated the interactions between the Tectomers and graphene oxide. After addition of Tectomers, either 2T or 4T, GO instantaneously flocculates, resulting in a colorless supernatant. SEM characterization of the flocculated GO sediments after being washed with water to remove the non-specifically bound material shows extensively coating of highly exfoliated graphene oxide on the rigid Tectomer platelets. Due to the two-dimensional structure of both Tectomers and GO, the interfacial interaction per unit area in these hybrids is maximized, leading to the formation of novel, unique, multi-layered assemblies. Epoxy and hydroxyl groups that extensively functionalize the basal plane of GO are capable of hydrogen bonding formation with the amino terminal groups of Tectomers. This has been confirmed by XPS characterization. We also studied the interaction of Tectomers and other carbon nanomaterials. Fluorescent nanodiamonds are attractive for in vitro and in vivo fluorescence imaging. These nanoparticles have abundant oxygen functional groups on the surface and attach well to the Tectomers, as confirmed by TEM. As for single-wall carbon nanohorns, and carbon nanocones, tectomers assist the dispersion in water of these highly hydrophobic nanomaterials. XPS spectra suggest that electron density donation from amino groups in tectomers to the pi system of carbon nanohorns and carbon nanocones occurs. We also tested tectomers and metal nanoparticles. Gold nanoparticles bear a negative charge due to the absorbed citrate molecules on their surface, and therefore effectively attached to the tectomers by electrostatic interactions with protonated amino groups. Indeed, the addition of tectomer solution makes the red gold nanoparticle solutions turn blue, as aggregation occurs due to the neutralization of the citrate charges around gold nanoparticles, resulting in gold tectomer precipitate. However, binding tectomers to iron nanoparticles further assisted iron nanoparticle dispersions, preventing iron nanoparticles aggregation. Here, the interaction both with carboxy and hydroxy groups on the carbon shell of iron nanoparticles come into play. Also, hybridization of tectomers with PVP functionalized platinum nanoparticles led to the formation of a stable platinum nanoparticle tectomer across dispersion. Finally, acrylate-based polymer nanoparticles were also studied. They form uniform and spherical nanoparticles around 160 nanometers in diameter with a high concentration of carboxylic groups. Such nanoparticles have been used as nanocarriers for dental applications by complexing them with metal cations such as calcium. We confirm by TEM that tectomers wrap around these polymer nanoparticles. Tectomer coating of GO fibers. GO fibers, 60 microns in diameter, were fabricated by wet spinning. GO fibers are macroscopic geo-layered assemblies that combine high mechanical strength and flexibility that allow them to be knitted into fabrics and complex three-dimensional architectures. Will tectomer efficiently coat GO fibers? The answer is yes. By immersion in tectomer solution, we obtained ultra-thin coatings of tectomers on GO fibers that, after drying, exhibited remarkable water-resistant properties. Moreover, we have exploited the strong hydrogen bond-based interaction between tectomers and GO to functionalize GO fiber surfaces with different carbon nanomaterials, using tectomers as double-sided sticky tape GO fiber decoration. For example, we observed that GO fibers fall apart upon immersion in carbon nanotube dispersions due to the well-known affinity between carbon nanotubes and GO. However, in the presence of tectomers, the fibers are not destroyed, as tectomers act like a protective layer. By conducting AFM, we measured an increase in GO fiber current density as a result of the carbon nanotube coatings. Such carbon nanotube tectomer coatings were extremely resistant to long water washing procedures. The simple procedure for carbon nanotube functionalization of GO fibers used here can be considered as an alternative approach to other strategies for carbon nanotube functionalization and coating of substrates. As in the case of carbon nanotubes, immersion of GO fibers in a fluorescent nanodiamond dispersion leads to the destruction of the fiber. However, tectomers again can act as a protective adhesive which allows fluorescent nanodiamond decoration of GO fibers. GO fibers were also decorated with carbon nanohorns and carbon nanocones. Poor material coatings were observed in the absence of Tectomer adhesive. Geofibers were decorated with metal nanoparticles, gold, platinum, and iron nanoparticles. And Tectomers provided enhanced nanoparticle adhesion and water-resistant properties. Also, this applies for polymer nanoparticles decoration of geofibers. Not only nanomaterials, but also molecules such as coralline and the potent anti-cancer drug doxorubicin efficiently attach to geofibers by means of tectomers and resist water washing procedures. Nanomaterial tectomer decoration of other fibers and fabrics. The use of tectomers adhesive for surface functionalization can be extended to other fibers and substrates. Thus, tectomers show good affinity to conducting PO, PDOT, PSS fibers. We used tectomers for functionalization of these fibers, for example, with gold nanoparticles. EDS shows efficient gold nanoparticle coating using tectomers as adhesives. Here we show PMMA fiber extensively coated with carbon nanohorns using tectomers as adhesives. And a polyester fabric. SEM images show that the density of carboxylated multi-wall carbon nanotubes on the fiber surface drastically increased when using tectomer adhesives. Two probe electrical resistant measurements showed that the carboxylated multi-wall carbon nanotubes coating provided electrical conductivity functionality to the fabric. The main conclusions of these studies are the following. Amino-terminal oligoglycine tectomers have a versatile surface chemistry that allows the fabrication of a variety of hybrid materials. Tectomers are successfully used as adhesives to stick different nanomaterials and molecules to geofibers, providing new fiber functionalities. Tectomer coatings are water resistant and protect the geofiber structure. This surface decoration strategy using tectomers is particularly interesting for smart textile applications. Thank you for your attention.